So we got this equation. Let's actually do a couple of checks to see whether the equation makes sense, and also see some special cases to get some physical intuition about the problem. Let's first do dimensional analysis. So if you can check, the left-hand side has the units of kelvins, right? It's the temperature. And the right-hand side, the first term is Kelvin minus times B times Kelvin. But let's check the dimensions of the B. And the B is, as you can see, minus Cp SVS rho S divided by CPF VF rho F, right? And all has the same units. So this the CP has the same unit as CPF, so they cancel. Basically, you get unitless. Or in other words, we actually show it. Oops. Yeah. No units. So the B doesn't have units, and here in this term, this is going to be Kelvin minus Kelvin divided by unitless. So you get Kelvin there, the first term. Plus, this is Kelvin, this is Kelvin, this is Kelvin, this is unitless. So this entire thing is Kelvin, right? Kelvin times the exponential, and the exponential is basically, you can check. This is unitless. You need to check the units of these things. Let's see whether they make sense. AS H 1 minus B over CPS VS rho S. AS has the units of meters squared, right? H has the units of watt per Kelvin, meter square Kelvin, right? 1 minus B is unitless, divided by the CP has the units of joules per Kelvin times kilogram, correct? So it's the energy needed to increase 1 Kelvin, increase the temperature of 1 kilogram material, 1 Kelvin. And the V has the units of meter cube, and the rho S is kilogram per meter cube. And if you can see, these cancel, Kelvins cancel, and you get basically these cancel. You get meter squared times meter squared. Meter squared times 1 over meter squared cancel. So you get watt over joules, but watt is basically joules per second. So this is just 1 over seconds. And in the exponential, so this is 1 over second, this is second, so that's unitless. So exponential unitless, that makes sense. If you're actually taking exponential of some number which has units, that means you're in trouble. If the argument of exponential has units, and that means you're doing something wrong. The the quantities inside exponential or sine or cosine brackets must be always unitless. Okay, so this makes sense. Now let's see some special cases. Let's check what is the temperature at T is equal to 0. Initially, when time is equal to 0, what's the temperature? Let's have a look at this equation again. As you can see, if you plug in time is equal to 0 here, then this becomes 0. This entire thing becomes 1, right? So you just get this quantity, right? So the Ts becomes plus minus Ts0 plus ETS0 divided by E. And this term has the same denominator. So you can add these terms, this cancel, these two cancel, and you get Ts is equal to Ts0, which makes sense because we know that initially the solid temperature must be the Ts0. Another special case, when T goes to infinity, what happens to this equation? This thing becomes negative infinity if T is infinity. Then that means the exponential of negative infinity is negligible, almost 0. So you can actually get rid of this term. And then it's just going to be this one. So let's write it down. Ts must be equal to Tf0 minus B Ts0 divided by 1 minus B. Okay? And that must be the equilibrium temperature. Right? That was one of the questions we asked. And this is the answer. For T goes to infinity, temperature goes to this quantity, which we're going to call as the equilibrium temperature. Now, let's see whether this makes sense by using another method to find the equilibrium temperature. T equilibrium. Well, during the equilibrium, what happens? Now it's going to be a steady state problem, right? Because nothing is going to change anymore. Everything settled down and all the temperatures came to their like steady state temperatures. Nothing is changing anymore. Nothing is changing with time and nothing is changing with position, right? And one way to do is the following. You can do a energy balance in minus out plus generation is equal to accumulation, right? And you can set the accumulation to 0, or you can say, okay, nothing is going to come in, nothing is going to come out. Okay. And nothing is being generated. Now here's the following. Let's do this for any time, but let's choose our system. choose the system, or choose the entire vessel as the system. So it's this thing which is basically adiabatic, insulated, no heat in, no heat out. It gives you the following equation at any time: in minus out plus generation is equal to accumulation. And let's say nothing is getting in, nothing is going out, nothing is being generated. So the accumulation must be 0. And the accumulation, you can think of it as the accumulation within the solid plus the accumulation within the fluid, right? It's basically the sum is 0, but separately the solid and the fluid might not be 0. And you can think of it as 0 is equal to the accumulation in the solid is going to be rho s times volume of the solid times Cp of the solid times the change in the temperature, which is the temperature of the solid minus the initial temperature of the solid. That's the amount of heat accumulated in the solid, plus the amount of heat accumulated in the fluid is rho fluid, V fluid, Cp fluid, T fluid minus Tf0. Okay. And from here, you can say what happens when it's equilibrium, right? When the system reaches equilibrium, what happens is Ts becomes equal to Tf, and that becomes equal to the equilibrium temperature. So the solid temperature becomes equal to the equilibrium temperature, and the fluid temperature also becomes equal to the equilibrium temperature, and they become equal to each other. So I'm going to replace this Ts by T equilibrium and this Tf by T equilibrium, and I'm going to solve for T equilibrium. Okay. So I'm going to have 0 is equal to rho s Vs Cps T equilibrium minus Ts0 plus, let me divide both sides by this rho f df Cpf as well. Then second term is going to be Tf, or T equilibrium, minus Tf0. Okay. And as you can actually distinguish, this is minus B, right? They called us the minus of that was B, so that's minus B. So you find 0 is equal to minus B plus 1 T equilibrium plus BTS0 minus TF0. And from here, if you solve for T equilibrium, you will find that T equilibrium is TF0 minus BTS0 divided by 1 minus B. And it's exactly the same thing as this match. Okay. So this makes sense. So I actually obtained the expected equilibrium temperature. Okay. Any questions so far? So let's call this special case 1. The special case 2. Now let's talk about another special case, which is special case 3. Is there any other special case that comes to your mind? What kind of like limiting cases can you think about? Like what extreme cases can you think about? Okay, if you don't have any idea, let me actually start the discussion. Large pool of liquid. Imagine an extreme case where you have a lot of liquids and the amount of solid is going to be negligible with respect to the liquid. So what does it mean? It means the following. The B term, which was equal to Vs rho s Cps divided by Vf rho f Cpf, right? Since this large pool of liquid means Vf goes to infinity, or Vf is much, much larger than Vs, then this thing goes to 0, right? Let's substitute B is equal to 0 in equation 3. Equation 3 was our solution, this one, right? Let's substitute B is equal to 0. And we find that if B is 0, then you get TF0 in this term. This would be TF0. And if this is 0, this is 0, this would be TS0 minus TF0, and the TF0s would cancel. You would get TS0 for the entire thing. I'm sorry. No. There's a multiplication here. Okay, let's go one by one. Okay. So TF0 in the first term, you get. So you get TS is equal to TF0 plus TS0 minus TF0 times exponential. Okay, so B is 0, so you just have this term here, minus ASH over CPS Vs rho s. T. Okay. And you can actually like rearrange this formula to have a non-dimensional number, non-dimensional temperature on the left-hand side, which is Ts minus Tf0 divided by Ts0 minus Tf0 is equal to exponential minus ASH over CPS Vs rho s T. Okay. And you can even simplify this further by calling this thing as 1 over tau, because I know that that quantity has inverse time units. So let me come up with like some characteristic time tau and call that 1 over tau. And the equation is Ts minus Tf0 divided by Ts0 minus Tf0 is equal to exponential minus T over tau. So tau is a positive number, a time constant or a characteristic time. Tau is called time constant or characteristic time, or it has another meaning. But first, let's have a look at this this formula. You can see that the TS0 gets closer and closer to TF0 because why? This is if you have a look at this exponential, as time increases, as time passes, you're going to see that this gets smaller and smaller and like attenuate to 0. And so you get this term getting more and more close to 0. And when this becomes close to 0, the numerator becomes almost 0. So the TS approaches the value of the TF0. Okay. Basically, the pool is so large that its temperature is not changing anymore. So it's only the solid temperature which is changing. And at the end, the solid temperature is going to be equal to the fluid temperature because the fluid volume is so high. And if you have a look at this thing, as we said, it's attenuating, and its function looks like the following. This is the exponential minus t over tau. And this tau is basically where this becomes equal to 1 over e. This function becomes 1 over e, which is like something like 0.5. This is tau. This is t-axis. This is 1. Okay. So basically, the tau tells you how fast the system is approaching, because if for another system you have this plot instead, then the tau is going to be something larger, right, for another system. And that means basically that system is cooling slower because the time scale is larger. It takes longer for the system to cool down. Okay. Okay. So this is tau 2. And tau 1 and tau 2 correspond to different systems. It's not for the same system. So if you, for example, take copper in some like 1 meter cube of water, like a small tiny copper placed in 1 meter cube of water, the fluid is so large. And then you have a particular tau 1, you should calculate from this expression because you know the AS, you know the H, you know the CPS, and so on. You have one particular tau, and you can calculate it for another system. For example, you can put this copper into not in water but some other fluids, and it's going to give you some different dynamics. Or maybe you can use mercury droplets instead of copper, and you're going to get a different tau, and it's going to tell you how fast the system is going to cool down. Okay, so you can think about this tau as a time scale for heat loss too. Or heat transfer. More correctly, heat transfer. Not necessarily it's losing heat. Okay, good. Okay, so you can actually dissociate this like t over tau into some other numbers. So let's make another page. Any questions so far? T over tau basically is going to tell us how close the temperature is to the equilibrium temperature, right? And that's basically equal to, as you know, the tau was the inverse of this AS H divided by CPS VS rho S T. Okay, and you can rearrange this formula and say it's H divided by Vs over As the volume divided by area of the sphere, CPS, rho s, times time. And you can rearrange this by, by calling this thing as L characteristic, because the volume divided by area gives you length dimensions, and it tells you something about the characteristic size of your system. Okay. And you can actually multiply by L characteristic numerator and multiply the denominator by L characteristic, and you can actually convert this into H L characteristic divided by K, and let's also divide by K and multiply by K to get KT divided by L characteristic squared CPS rho s. Okay, and there is another thing here, K over rho CP, which has a particular name which you should know. K over rho CP is called thermal diffusivity. And we abbreviate it using alpha. Okay. It tells you how fast is the heat dissipated. Okay. And if you actually replace this quantity with alpha, which is the thermal diffusivity, you find out that T over tau can be written as HL characteristic divided by K times alpha T, maybe alpha, over L characteristic times T. Okay. And this number, actually, you know the meaning of this number, right? So this one. What was the name of this number? We actually called it HR over K instead of HL characteristic over K, but doesn't matter. It's H times some length divided by conductivity. That's called, anybody who follows?
The bio number?
The bio number, excellent. So this is called the bio number. And the second number, the second factor, is something new. We're going to call it Fourier number. Oops. And it gives you an idea about how much of time elapsed in units of characteristic times. Not exactly, but it's proportional to that. And yeah. Any questions so far?
That L characteristic, should it be squared?
Yep, it should be. Thank you. Thank you for the correction. Exactly. It's alpha over L characteristic squared times time. Do you want to have do you want to solve like a numerical problem just to make things more clear and concrete? What do you think? Would that help?
Yeah, can we solve like a numerical one since we haven't really done anything like that?
Yeah, so we derived the equations. Now we can actually come up with a system where we know the material, we know the numbers and so on. Let's see how we can make use of these formulas, right? So I'm just going to make up a problem. Okay. Example. Imagine you have a copper, but I would actually ask you to find the numbers for those, okay? So this is copper sphere. It has a radius, radius, what's going on? Okay. Okay, good. Radius of 2 centimeters, okay? And its conductivity is, let's Google it. Anybody, you can find the conductivity of copper. At 20, for example, centigrade. But we need to look for thermal conductivity. Okay. So let's take the K as 398 watts per meter Kelvin. Okay. And initial temperature of the copper is given as, for example, it's so hot it's 100 degrees centigrade, or in other words, roughly 373 Kelvin. Okay. Let's find how much will the temperature be, TSB, at, look, after 10 seconds, 10 minutes, and 10 hours. Okay, let's see. And let me give the age. Okay, age. It's in an environment, so let's think about this like a well circulating air at TF is equal to 273 Kelvin. Okay, and H you can take approximately as 10 watts per meter square Kelvin. Okay, let's first check the assumption that the temperature is going to stay uniform along the copper. And it's only going to change with time, but not with position. So let's calculate the bio number. H. You can use HR over K or HL characteristic over K, but let's use, since we know the geometry, I think it's better to do L characteristic over K. It's not going to matter in I mean, you're going to get the same order of magnitude for either way. Okay, and let's write down the volume. So this is the question. The volume of the sphere is 4 over 3 pi r cubed, which is 4 over 3 pi times 2 times 10 to minus 2 meters cubed. Okay. Okay. Somebody who has calculator can help me, I guess. This is 3.35 times 10 to minus 5 meter square, correct? Oh, sorry, meter cube, meters cube. And the area of the surface of the copper is 4 pi r squared, which is 4 pi 2 times 10 to minus 2 meters squared, and you get pi times 4. .03 times 10 to minus 3 meters squared, and the characteristic length becomes equal to Vs over As, which is let's see, 3.35. Okay. .66, yeah, times 10 to minus 3. Yep, meters. Okay, there we go. So now we can calculate the bio number. Which is H10 watt per meter square Kelvin times L characteristics is 6.66 times 10 to minus 3 meter divided by K is 398 watt per meter Kelvin, and you get something like, okay, times 10 divided by 398. There you go. 1.67 10 to minus 4, correct? And it's much smaller than 1, so we can assume T solid is a function of time only, right? Now we can actually use the formula that we derived, that Ts minus Tf0 for large amount of air surrounding, Ts minus Tf0 divided by Ts0 minus Tf0 is equal to exponential minus T over tau, right? And the T over tau, I can write it as bio number times Fourier number. And the Fourier number for the first case is equal to alpha over L square characteristic time. And alpha is basically K over rho Cp we should find the values for the Cp and rho of the copper 2. So let's write them here. Rho copper is equal to roughly in SI units. That's going to be 8,960 kilogram per meter cube. And the CP copper in joules per kilogram, it's going to be 385 joules per kilogram in SI units. Okay, good. So times time, K is 398 watt per meter Kelvin, divided by the L characteristic, 6.66 times 10 to minus 3 meter squared. CPS is 385 joules per kilogram, and rho S is 8,960. Okay, and the time T1 is 10 seconds. Okay. So let's do this calculation. 398 times 10 times. Okay, and times. Okay, something around 26. 26. And yeah, it's unitless, 26, the Fourier number. And so for the first case, after 10 seconds, Ts minus Tf0 is 273 Kelvin divided by Ts0 is 373 Kelvin minus 273 Kelvin is equal to exponential minus the Bio number times the Fourier number. The Bio number we found it's 1.67 times 10 to minus 4 times the Fourier number is 26. Okay. And then you would get Ts is equal to, let's see, exponential. Oops. Okay. Let's see. Okay. Can somebody do this calculation for me, please? Somehow I don't, for some reason, I don't have my calculator with me. And it's really difficult to do with the computer.
I got 372.5.
372.5
0.5.
Kelvin. Okay, good. If you do it after 10 minutes, it's going to be, I guess, like 60 times longer. So the Fourier number is going to be 60 times 26, the previous one. So you would calculate the same thing for this, and you're going to get a smaller and smaller number, and it's going to approach the 273 as time increased. Okay, so that might be a good exercise for you. So do it for, so this is TS, 10 seconds. Please do it for TS. T is equal to 10 minutes, and TS, T is equal to 10 hours. Okay? As a homework not to be collected.